Oh, it's frozen. Okay, thank you. All right, so all of 4.6 is going to be some kind of transformation of the parent functions. So you'll be using this sheet for weeks probably. So I just want you to note that this is just an informational sheet that we're going to fill out. So you will be successful. You can measure success when you can graph a parent function and you can identify its critical pieces of information. Okay? And remember that a parent function, you've heard of these before? This should be a review. Hopefully it'll come back to you. I know it's been a year. Parent functions are just the most basic or simplest form of any function family. So like there's the linear function family, where the parent, the dad says to the mom, "Oh, honey, look, he has your slope." Or the parent function of the quadratic mom's dad says to the mom, "Oh, honey, guess what? She's got your curves." Okay, so basically what we're talking about is the most basic form of any type of function family. Lines graph lines, quadratics graph parabolas, cubics graph, you know, the curves, etc. So we're going to talk about all the basics. So here we start with the linear function, y equals x, or f of x, the function of x is x. Now my intention is for you to immediately slap this guy down on a graph. You know exactly what this graph looks like. You know exactly where it goes. It is tattooed on your brain. Whatever x is, y is. So I've given you a number of points that you can plug in for y equals x. Remember that we can replace that with a y. Okay, so if x is -2, y is? If x is -1, 0 is 0, 1 is 1, 2 is 2, 3 is 3. They are identical inputs and outputs. So when I go to graph that, it just cuts right across your graph. It increases, increases, increases. Okay? We need you to be at the point now in math analysis where you are just getting that guy graphed. That's the parent function. If I change the slope, it becomes a family member, like a kid or a cousin or whatever. But if it's got an x to the first power and a y to the first power, it's supposed to graph a diagonal line. Okay, so let's talk about its x-intercept. 0, 0, which means it's also its y-intercept because most parent functions are going to have that as a starting point. Okay, let's talk about its domain. Is there any x I'm not allowed to plug into the equation? Unrestricted, so from -infinity to infinity. How about our range? Whatever x is, y is, so whatever the domain is, the range is. Okay, so now, do we call this a continuous graph or a discontinuous graph? Continuous. It doesn't have a break in the graph. Now, here's where I'm going to address whether it's even, odd, or neither, and we're going to talk about the type of symmetry it has. Now, I've given you some tips on how to immediately determine if it's even, odd, or neither, but let's go into a little more detail by using the mathematical proof that this is actually an odd function. Now, to prove that it's an odd function or an even function, or neither, what you do is you plug in the opposite of the original function. So we're going to plug in the opposite of x, or a -x. When I do that, and I simplify that, what's the opposite of -x? Or no, what is 1 times -x? -x. So this solution is exactly opposite of the original function. This is the test that says that this is definitely an odd function. Now, what does that mean when it comes to symmetry? Okay, So if a function has odd, if it's an odd function, it has rotational symmetry around the origin. So I'm going to tell you that it's symmetric about the origin, but it doesn't have like foldable symmetry. It has rotational symmetry. So it's a 180 degree, and that doesn't matter clockwise or counterclockwise. 180 degree just means you're rotating it upside down. So it's 180 degree rotational symmetry. So I'm going to prove that here by seeing if it'll let me just grab sometimes it won't let me do that. I'm going to shorten my little line up just a little bit. So you can see that if I take, can I just have this one? No, I don't want that. Oh man, why when I'm making videos will you not cooperate? Try again. I don't want to rotate all that because it messes everything up. Okay, and try one more time. I'm going to get that out of the way, and I'm going to get that out of the way, and that out of the way. One more time. Okay. Cross your fingers. There it is. Okay. I'm going to rotate it 180 degrees. I got to get it exactly 180 degrees. It's almost there. There it is. It's upside down. It's exactly the same graph. It mapped right on top of itself. So visually you can see that I took the point 1.1 or 1, and I rotated it 180 degrees. So now that it's on -1, -1. I took 2, and I rotated it 180 degrees to -2, -2, etc. And you can also see it down here on your table of values. Okay, this is really helpful because you don't want to sit and try to rotate your paper around, but that's one way to do it. It's just to take your paper and flip it upside down and see if it still looks the same. That's the fastest way to check. I can't rotate my paper. Okay, but here, look at my points. Corresponding to -2, -2 is +2, +2. They're exact opposites. So for example, just so we're really clear, if I take the point -3, 2, and I rotate it 180 degrees, where am I going to land? At 3, -2. So -3, +2 corresponds to 3, -2. So what did the signs on the X and Y values do? They both switch. Okay, so that's what we call rotational symmetry 180 degrees. So you can see it happening down here on your corresponding parts. Okay, does it have a maximum? Back to filling out our chart. Does a peak or a valley? So not applicable here. It doesn't have any of those. Okay, how about intervals of increasing? What is this graph doing as I read it left to right all the time, all the time? It's increasing. If I start at -infinity, it's always going to be rising all the way to +infinity. So it does not have an interval of decreasing. Okay, all critical information here. Now let's talk about our end behaviors. As x approaches -infinity, f of x approaches, and this should happen. It's an odd degree function. It's a degree of 1 function, so it's end behaviors. Okay, should be doing what's happening here. As x goes positive, your y is going positive. So your end behaviors on odd degree functions should be going in opposite directions. Okay, so there's the linear parent function. Doesn't have any numbers in it. It's just an x and a y. So that's the basic equation of a line. Okay, here we go. The basic or the parent function of the quadratic says y equals x squared, or f of x equals x squared. Okay, so let's start with our table of values for y equals x squared. So if I square -3, I get -2, -1, 0, 1, 2. Good. Okay, so, right? Very basic numbers. You're just squaring your positives and negatives. So -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And then you can go ahead and reflect 3, 9. And draw your parabola. Basic parabola here. The parent of all parabolas. Right here, the granddaddy. Right there. Oh, but that's a grandparent. Okay, the mom or the dad, whatever. They're both the same. There they are. That's the parent function for the quadratic. Okay, so what kind of x-intercept does it have? A zeros. 0, 0, which means it's also its y-intercept. Talk about the domain. Anything restricted? Is there anything I'm not allowed to square? I can square anything I want. However, I can't get negatives out when I square, right? 0 to infinity. I can't square a negative and get a negative. If I square a negative, look, I squared a -3, I get a +9. Lowest value I could get was 0. Is it continuous? You bet. No break in the graph. So now let's determine what kind of symmetry it has. Again, the test is to plug in a negative x. So I'm going to do the f of -x is equal to a -x squared, like so. Okay, now simplify that. Do the math. What is -x squared? It's x squared. -x times -x is +x squared. That is exactly the same as it was to begin with. Because when I square a negative versus when I square a positive, I always get the same positive result. Therefore, we would call this an even function. It has symmetry. It's foldable symmetry. Where is it symmetric? The y-axis. The equation of the y-axis is x equals 0, but it is really symmetric. If we're being precise, it's symmetric across about x equals 0, but we call that the y-axis. Whatever we graph to the left, we graph to the right. Does not have a maximum, but it does have a minimum at 0, 0. Okay, so intervals of increasing. So we hit the valley, so it's decreasing until we hit the valley, and then it increases, right? So increasing from, increasing, 0 to infinity, decreasing, -infinity to 0. But not inclusive of 0 because 0, 0 is actually not an increase or a decrease, it's just the bottom. These are all parentheses. Sorry. Sorry about that. Okay, in behaviors. Since this is an even degree, it's a degree of 2, the end behavior should be the same. If it's a degree of odd degree, then the end behavior should be opposite. So let's do this. As x approaches -infinity, what's your y approaching? Infinity. It's going up. As x approaches +infinity, infinity, because that 2 is an even degree, so the ends have to go in the same direction. Cubic. Okay, here's where you need your calculator because I'm not going to do it for you. You have to train yourself to do this graph. Okay, so this is the cubic function f of x equals x cubed. Degree 3. Possible turning points? 2, but maybe not. That's the maximum turning points. There's not a lot going on in this equation. It's a basic, the most basic cubic function. So here are the points I gave you. I gave you -1.5, -1, -0.5, 0, 1.5, 1, and 1.5. And here's the reason I didn't give you 2. Because what's 2 cubed? 8. I'm already off of my graph. Your graph only goes up and down 6, right? So that's why I didn't give you a 2. So we're going to go y is equal to x cubed, plug in a negative 1.5 and cube it. Negative 3.375. So let's just use our brain. What's positive 1.5 cubed? 3 point. You got it. Positive 3.375. Okay, let's do negative 1 cubed. In your head, negative 1 times negative 1 times negative 1. Negative 1. So positive 1 cubed is positive 1. Now go do negative half cubed. Negative 0. Okay, so positive 0.5 is positive. And 0 cubed is 0. Okay, so we filled out our table of values. Let's go graph those points. So negative 1.5, negative 3.375. Negative 1, negative 1, negative half, negative barely below the line, right? 0, 0. And then everything starts turning and going the other way. And then it shoots way off the graph. 2, 8, negative 2, negative 8, positive 2, positive 8. It gets really steep, right? Because imagine 4 cubed. That's 64. 5 cubed, 125. 6 cubed, 216. It gets really steep. But at 0, 0 is a little bit of a turning point there. Okay? So it's got a 0, 0 intercepts, your origins, and let's talk about your domain. What do you think? Anything I'm not allowed to cube? Any restrictions on my domain? Nope. How about on my range?
Yeah. Oh,
If I cube a negative, I get a really big negative. If I cube a positive, I get a really big positive. If I cube 0, I get 0. So, why did I write 0, 0 for my domain? Sorry. Negative infinity to infinity. Okay, Mrs. Frame. Your range is also unrestricted. Okay, is it continuous or discontinuous?
Continuous.
Okay, now let's do the test to see if it's even, odd, or neither. So if I plug in a negative x, that's a negative x quantity cubed. Do the math. What's negative x times negative x times negative x? Negative x cubed, which is the opposite of positive x cubed. So that means it is odd. So it's symmetric about 0, 0 with 180-degree rotation. And you can see it again in the table of values, right? Negative 1.5 was negative 3.3. Positive 1.5 was positive 3.3, right? This just rotated to there 180 degrees. This rotated to there. This one rotated to there. They all rotated at 180 degrees. I'm not going to flip it around. Okay, maximums. It doesn't have any peaks, and it doesn't have any values. I mean, valleys. It has lots of values. Okay, intervals of increasing. Now, when you look at this is increasing, right? And then it starts to change direction, but it's still, and then it starts to get really steep again, but it's always increasing. That's right. There is no decrease. None. It's just always from left to right, increase, increase, increase. Let's talk about our end behaviors if you're ready. As I approach negative infinity on my x, my y approaches. And since this is an odd degree, should my other end go in the opposite direction? Yep, it's a degree of 3. As x goes to positive infinity, y is also approaching positive infinity. All these little critical pieces of information. Okay. Here we go. Last one for this side of the sheet, the square root function. And let's go a little bit quicker, okay? So I've asked you for the f of x equals the square root of x. And I've given you these values for your x. Negative 1, 0, 1, 4, and 9. So y is equal to the square root of x. And I want you to, just even though you know, I want you to plug the square root of -1 into your calculator. Do it. Calculator's going to give you a message that's really important for you to be able to translate into English. What does it say? Domain error, which means it's a domain restriction. Not allowed to put negatives under square root. So I know that's an error. What if I plug in the square root of 0? 1, square root of 4, square root of 9. All right. So we're going to graph 0, 0, 1, 1, 4, 2, and 9, 3. Okay. All right. So let's talk about our x-intercept.
0.
X-intercept.
Oh, sorry.
The origin, right? And the y-intercept's also the origin. So far, that's been the same on the parent function. So our basic function here, what's our domain? 0 inclusive to infinity. And if 0 is our lowest x, what's our lowest y? 0 to infinity. All right. Is this graph continuous or discontinuous? In one direction, right? Continuous in one direction. Now, is it even, odd, or neither? How do we test? Plug in the opposite of x. So if I do that, will I get the same outcome as if I plug in a positive x? So we would say this is neither, it doesn't have the kind of symmetry. We're looking for neither even or odd. So symmetric about, that is not applicable. And you can see this graph does not have symmetry. If I flip it upside down, it's going to go like that. Actually, if I rotate it, it's going to go like that. If I flip it upside down, it's going to go like that. But, and if I can also flip it that way and it goes like that. But that's not part of the original graph. Okay. Maximum. Does it have one? How about a minimum? 0, 0. That's your starting point. Okay, and it's always increasing starting at x equals 0. So starting at 0, it's going up forever. Is it inclusive of 0? If you were to put a parentheses on that, I wouldn't be mad about that. Doesn't have a decreasing. Okay, there is a typo here because can x approach negative infinity? What is the smallest value x can approach? So as x approaches 0, so let's change that to a 0. What's my y approaching? So as I go this way, what's my y doing? It's approaching 0. Yeah, it's not approaching negative infinity. And as x approaches positive infinity, y approaches infinity. Okay, absolute value. This is the last one that's probably going to be really familiar. And we need to finish. We got about 11 minutes, so let's do it. So we have f of x is equal to the absolute value of x. Again, it's the basic absolute value function. No numbers. Just y equals the absolute value of x. So absolute value of -2, people. Plug it in your table of values. 2. Absolute value of -1. Absolute value of 0. Absolute value of 1. Absolute value of 2. There we go. Okay. Some of you are faster at math than others. Okay, so we're going to graph that. So it's a lot like the parent linear function, except when it gets to 0, 0, instead of continuing down, turns and goes the opposite direction. Oh, that line got crooked. Let me fix that. No, it didn't. We're good. Okay. X-intercept, y-intercept are both the origin. So let's talk about our domain. Any restrictions from what I can put inside an absolute value? I can put anything I want in, but what can I not get out of an absolute value? Negatives. So the range is the lowest value, 0, yep, to infinity. Continuous or discontinuous? by looking at it, even, odd, or neither. Does it have symmetry on the y-axis? Guess what it is? How do we know that? If we plug in a negative x, we get a positive x. Just like up here, we get a positive x. So they're same. So it's even though it doesn't have an even exponent. So a little tweak from what we learned before. So it's symmetric about x equals 0, which is our y-axis. Does not have a maximum, but does have a minimum. Okay, increasing from 0 to infinity, decreasing from negative infinity to 0. Okay, since it's even, the end behaviors have to go in the same direction, don't they? So as x approaches negative infinity, y approaches, and the same thing on the right. The further right we go, the higher we go. The further left we go, the higher we go. Okay, so that's the end of the basic ones. We're going to do 3 more. The rational function, which on next Wednesday you will get we'll dive really far into this. We're going to get it graphed right now anyway. And now you're starting to see numbers appear in the basic parent function. So the rational function, f of x is equal to 1 over x. We're going to have to start watching for restrictions. We're going to have to graph some asymptotes in here. So I've given you some points to plug in to y equals 1 over x. So I want you to imagine that I put a negative 2 in the denominator. What's 1 divided by negative 2? Negative half. Yep. What's 1 divided by negative 1? 1 divided by 0. Domain error. Can't put 0 in the denominator. So we have a domain restriction. 1 divided by 1. 1 divided by 2. 1 divided by 3. 1 divided by 4. 1 divided by a million. 1 divided by a billion. Am I ever going to get to 0? Or am I going to get to the most teeny fractions of numbers? But I'm never going to hit 0. It doesn't matter what I put in the denominator. I'm never going to hit 0. I can go negative. I can go positive, but I can never hit 0. Okay, so I'm thinking no x-intercept, no y-intercept. Let's not graph yet. Let's come up here to our domain. What are we restricted from? So our domain is going to be from negative infinity approaching 0. Union, you got it, 0 to infinity. So I'm going to grab my red pen that I told you to get out a while ago, and I am going to deny x equals 0 because that is against the rules of a fraction. Okay? Now, it's possible that over here, am I ever going to get a 0 in my y's? No, right? I can go really negative. I can go really positive, but I can never reach 0. And so my range is also restricted from the x-axis. And that in another way, can I ever take 1 and divide it by some number and make it equal 0? 1 divided by something is always something that's not 0. So our range is also a union that's non-inclusive of 0. Okay, so now what I'm going to do is I'm going to go ahead and I'm going to determine if it's continuous or discontinuous. What do you think? It's discontinuous because over here, I'm going to go 2, negative half, negative 1, negative 1. I'll do negative half, negative 2. It's all going to graph down here in quadrant 3. And then I'm not allowed to graph right here. Then I go over here and all of these pictures or all of this graph is going to be up here in quadrant 1. I'm not going to have anything in quadrant 2, nothing in quadrant 3. Okay, so we would call this a discontinuous graph. It's got a break in it. You have to actually pick up your pencil because you can't cross the red line. You have to pick up your pencil and hop over it. Okay, Is it even, odd, or neither? Let's do the test. The f of negative x is equal to 1 over negative x. Simplify. Yeah, positive divided by negative is negative. This is opposite of that. Therefore, it is odd. Whatever I graph in quadrant 1, I'm going to graph corresponding in quadrant 3 because they got to go 180 degrees. Okay, so let's go ahead and graph 1, 1, and 2 half, and 3/3, and you could do 4 1/4, but by then you're getting so close to your line, it's probably hard to tell. And let's also do this one. Ready? Half 2, 1/3 3, just so you have all those nice little points in there. Okay, and let's do the same thing over here. We're doing, so here I did this, half 2. So its corresponding part is negative half, negative 2. I did 1/3 3, so negative 1/3 down 3. 1, 1, negative 1, negative 1. 2 half, negative 2, negative half, and then negative 1/3. So your graph is going to approach these little red lines. And at some point, of course, your pencil is not fine enough. You will at some point run into those lines. So stop drawing and just put arrows. And then do the same thing down here. Now, can you imagine me rotating this 180 degrees? Don't you think it would look exactly the same? Okay, so it's symmetric about the origin, and it has 180 degree rotational symmetry. Okay, no x-intercept, no y-intercept. We're denied from touching them according to our restrictions. No maxes, no mins. Now, let's talk about the intervals of increasing. As I read this left to right, what's it doing? Forever. That's a decrease. As I read this side, left to right, what's it doing? They are both decreasing, except there's a break. So there's no increase. And it's decreasing from negative infinity to 0. Union with the other side, 0 to infinity. So it's got that break in it, discontinuous. In behaviors, be careful. As x approaches negative infinity, what's my y doing? Getting closer and closer to 0. Yep, as I go this way, look, I'm getting closer and closer to 0, but am I allowed to touch it? No, I can only approach it. How about this way? As x goes to positive infinity, what's my y doing? It's approaching the other side of 0. Okay, so the bell's about to ring. So we will hang on to the exponential and the logarithmic until tomorrow because we don't really need them until after Valentine's Day anyway.